Okay, this is part 2, section 5.3. We're looking at independence and the multiplication rule. So we're going to look at the reliability and how probabilities can go or be implemented and applied to this concept. So we have a parallel structure of identical components, and the system can exceed if at least one of the components succeeds. So we have two components that are running in parallel, and as long as at least one of those components succeeds, then the entire structure will succeed. Assume that components fail independently of each other, and that each component has a 0.15 probability or 15% chance of failure. So would it be, the first question, would it be unusual for one component to fail? Okay, so this is just, what's the probability that one component fails? Okay, that's just simply the 0.15. Is that unusual? In this case, no, because again, for a lot of the questions we look at, anything less than 5% is unusual, so 15% is not unusual. However, what's the probability that two fail? Okay, well, they're independent, so we can multiply the probability the first fails and the probability the second fails, which when I multiply these together, I get a 0.0225, and that is unusual because that is less than 5% or 0.05. So we've got this parallel structure, and it's very unusual to see two components fail, but to see one component fail, that's not unusual. So that's part A. Now, my pencil just died. One sec. I think it's trying to bring it back to life. Okay. So now we're looking at what's the probability that a parallel structure with two identical components will succeed. So in order for this thing to succeed, we just need at least one of the components to hold on. So the success is at least one works. Well, there's different scenarios for that. You could have, say there's a left and a right component. You could have the left work and the right fail. You could have the right work and the left fail. You could have them both working. So you have multiple scenarios. So this is where the complement rule is going to happen. So the probability that they both, or at least one succeeds, or at least one works, the complement of that is 1 minus the probability that both fail. Okay, and we know the probability that of both of them failing is the 0.0225. So this would be 1 minus 0.0225, which is 0.9775. Okay, so that's a probability that this parallel structure with two identical components will succeed. Now, this last question is going to make us think for a minute. So how many components would be needed in the structure so that the probability the system will succeed is greater than 0.9999? So again, for it to succeed, we need at least one of the components to succeed. So again, remember the probability that we succeed is that we just need at least one success is one we could think of it. So the probability of at least one success, again, is 1 minus the probability that none of them succeed. Or in other words, we don't know how many, so we'll just say n for the number, the probability that n fail. And n is going to be the number of components we would need so that this structure succeeds with that probability of 0.9999. So again, we want this success, so this is going to be 0.9999 equals 1 minus the probability that n fail and they're independent is going to be 0.15 raised to the nth power. Again, because if you think about that, the probability that all of them fail, you'll just take the 15% times 15% for n components. But we want this success, so we want the probability that at least one of them succeeds is 0.9999. Now, to solve this equation, okay, what we would need to do is we would need to isolate our variable. So I'm going to add the 0.15 to the n to both sides, just to make that positive, and then I'll subtract the 0.9999. So that we zero out here. So I'd get 0.15 to the n equals 1 minus 0.9999, or 0.15 to the n equals 0.0001. So now the question is what is n? And this is the number of components we need. Well, 0.15 to what power is equal to 0.0001? There are ways to solve this precisely. We would use logarithms, but if you're not familiar with logarithms, what you would just do is kind of use the guess and check method would probably be a simple way. And if you plug in n equals 4, if you do 0.15 to the 4th power, then you get 0.0005, which is just a little bit bigger than the 0.0001. And then if I do n equals 5, 0.15 to the 5th power, I get 0.00008. And you can see that 0.0001 falls somewhere in between there. So in this case, you would need at least 5 components. So if you were building a system and you wanted to succeed at that 0.9999 probability, and you know the fail rate of 1 and they're independent, then you want your structure to have at least 5 components to ensure that probability. So this would help if you were trying to build something, because of course you could overkill it. You could put 10 of them in there and feel pretty confident, but that could be costly. Say each of these components, maybe they each cost $10 million. So if you overbuild, that's a pretty substantial investment. So if you know the numbers and you can do a little bit of calculation with the probabilities, then you could minimize your cost while maximizing your probability or likelihood for success. So that's a look at independent events and the multiplication rule. If you have any questions, let me know.